Now we're going to have the second talk of the evening by Manish about zero-copy deserialization and how to make it screaming fast. Please.
So hi everyone, I'm Manish. I work on the internationalization team here at Google. I'm going to be taking you all through a journey of zero-copy deserialization. Join me and I'll show you just how deep the rabbit hole goes. A bit about me first. I've been at Rustacean for 8 years, back from the days when Rust was less stable than your average azo, tetrazole. It still pretended to have a garbage collector. It never did. It was always broken. I also created Rust Clippy, known for being the most annoying tool in the Rust universe. It's been the single greatest act of petard hoisting I've ever committed. It hates my own code, so yeah. I currently head up the Rust DevTools team. I also think that languages, both computer and human, are pretty neat. Yeah. To give you an idea of the flow of this talk, I'm going to start out by talking a bit about why we care about deserialization. Shane already talked a bunch about this, but I kind of want to go through an example. Then I'm going to explain the concept of zero-copy deserialization. And then finally, I'm going to try to address 3 questions about zero-copy deserialization. Can we make it work for more things? Can we make it pleasant to use? And can we even avoid it altogether? So I work on ICU4X. Earlier, my colleague Shane introduced ICU4X. But for those who are maybe watching this online or got there in the middle of the talk, ICU4X is a new modular internationalization library in Rust. As an internationalization library, we answer questions like, how do you format this date in French in Canada with the Gregorian calendar? Or how would this list be sorted in Japanese? Or how do you format this number in Marathi? This needs a ton of per locale data. Let me demonstrate. As I just mentioned, one thing we do is formatting dates. For example, you can give ICU4X a certain time and ask it to format it a couple of different ways for American English and for Bangla. So here are the 2. You can see a bunch of formats. Some of them are really long, some of them are short. You can see the American English one is month first and then date. But the Bangla one, if you can read those numbers, is the reverse. Let's look at just one of these date formats across the 2 locales.
You move a little to your right.
Oh, yes. Let's look at one of these 2 date formats across the 2 locales. What data do we need to produce? Just these 2. First, we need to know how to format the day of the week. We need to have the string Tuesday from somewhere. So here's the data needed for formatting the day of the week. You can see that there's some short ones, some really short ones, medium-sized, and long ones, depending on how big you want the day of the week to be. What else? You also need the month. And here's the data for that. I know the font's small. You don't actually need to be able to read it, just to give an idea of the size of the data. What else? You need to know what the digits look like for the requested language. And that's not that complicated, just 10 digits, nothing fancy. What else? You need to know the order to display everything in. If you look closely, you'll notice that in American English, it's October 11th, but in Bengali, it's 11 October. They're swapped. Here's the data needed for those. This contains things about ordering, but it also contains things like MMDDYY and DDMMYY, which is also just a kind of ordering. It also tells you kind of how to combine day and date and time when you need to put them together. There's more if you want to format things like eras, like AD or CE or whatever. For example, these dates are formatted such that they also need era data, which looks kind of like this. And this was just showing off some of the data needed for a single ICU4X component, date formatting, date time formatting. We have a whole host of useful operations, each with its own requirements for internationalization data. So we care about data quite a bit. We have a lot of data. We need to handle it. One of our goals is that we're modular in both code and data. We want to give you the flexibility of how much data you load, how you load it, and when you load it. The main strategy we employ for this is deserialization. The data is some format like JSON or James Munn's postcard, and you can fetch it however you want. You can get it on demand over the network, from the file system, whatever. And then you use a deserialization library to load it into memory. In Rust, usually deserialization looks something like this. Most people use the Zürisee library. There are some others. You slap this custom derive on your type, and that makes them serializable. And then you can just load data with Zürisee plugins. Unfortunately, the deserialization has a cost. If the text at the right is a snippet of a JSON file in memory that's being deserialized, every time you deserialize this person type, Rust needs to allocate space for that string and then copy it over. For a single string, this is not that expensive, but if you looked at the size of data ICU4X needs, this starts becoming a cost. Zürisee does support zero-copy deserialization. And what happens in zero-copy deserialization is, in Rust especially, is you add a Rust lifetime to indicate borrowing. You also add this special attribute. And with this setup, when deserializing, Zürisee can simply validate that the data in the file represents in the loaded file represents a valid string. It'll just look at that, be like, that's correct, UTF-8, great. And then it'll just take a reference to that data itself that's already loaded in memory as part of the file. This happened without an allocation or a string copy. Instead, person just holds a reference to the original blob of data it was deserializing from. This is significantly cheaper if you have a lot of strings or some large strings. You can just load the file into memory, and then deserialization is just making a bunch of pointers much faster. And of course, it's much cheaper on memory because you're never allocating except for the original loading of the file into memory. You might have noticed that I switched over to a binary format postcard in the lines below. This is because human-readable formats like JSON often contain things like escape sequences. And zero-copy deserialization doesn't work with that because the escape sequence will now be like a backslash and an N or something in memory, and you want the actual new line character in your string. If you want stuff to work with both human-readable and binary data formats, you typically use something like, you use these owned or borrowed types like cow, so that you can kind of copy it into memory for the human readable form, copy it into an allocation for the human readable formats, but still take a reference for JSON, for binary formats. It's just good practice to use cow and cow-like types everywhere when doing zero-copy deserialization. Overall, the basic idea of zero-copy deserialization is that deserialization should be just a pure, cheap validation step. It shouldn't do any allocations or major copies. So zero-copy deserialization is cool and all, but out of the box, it's got limitations. One is around collections. We had some simple data in the earlier example, but what about the datetime stuff we talked about? We'd like to store all of that data in a zero-copy fashion, and we'd need something like this. Like a bunch of month names, a bunch of weekday names, a bunch of digits. We'd also need some way to do this kind of nested cow in a way that's still zero-copy, because now this is a slice of strings, we'd need some kind of cow of something that works. This doesn't work in Zürisee by default, and there are a bunch of different reasons why. There are separate problems for sized data, like char and U8, and unsized data like string. Let's walk through a bit of why this is tricky. Let's look at sized data first. Suppose we have a buffer of U32s that we're trying to deserialize. Let's say this buffer. There are two ways this slice could get represented in memory as a series of bytes. The first way would be with the most significant bits first, like this. Pretty straightforward, right? The other way would be with the least significant bits first, like this. Feels kind of backwards. These two approaches are called big endian and little endian, and they're actually originally named after terminology from the novel Gulliver's Travels. They refer to the end of the hard-boiled egg that a person cracks when eating. Personally, I don't actually do either. I crack them on their side, which makes me like middle endian or something. And this seems to be normal amongst Americans because we don't use egg cups, so it doesn't matter how you just put it on your plate and eat it. And that's the kind of stuff you get to think about when you work in internationalization. Anyway, back to endianness. Most systems these days are little endian, which is the backwards one, but big endian systems do exist. This is a problem for zero-copy deserialization. The whole point of it is that you can directly refer to a region of memory from the serialized data and have it work, but the same U32 integer is represented differently on different platforms, so the same data file can't be used on both. This is only a problem around slices, bear in mind. With plain U32s, they need to be copied out anyway, so the deserialization can handle the change of endianness if needed. So you can still use U32s with zero-copy deserialization, you just can't put them in slices. And it's worth pointing out that when we say zero copy, it's a bit of a misnomer. What it really is it's zero allocations or zero large copies. All your normal like primitives and copy types are still getting copied, but your vectors and strings and stuff are being just validated. Another issue is alignment. Let's look at this array again. Most types in Rust and other systems languages have a required alignment. For example, U32s can only exist at memory addresses that are multiples of 4. But if we're deserializing data from a larger serialized blob, there's going to be data before and after it, and we don't actually know where it's going to end up. So it may or may not be aligned. We could maybe have our serialization format insert padding specially, and then pinky promise that the original data was loaded aligned. This isn't super safe, and it doesn't really work well with Zürisee's model. There are other crates that do this kind of thing, but it doesn't work with Zürisee, and we kind of wanted to use Zürisee, which is somewhat of the standard amongst the Rust community. All right, so those were the problems with fixed size data. What about variable size data? Let's say we want to do a slice of strings, like the slice of month names. In memory, it might look something like this, with each element being some pointer and a length. That's going to expand to something like this when viewed as a list of integers. And then the 2 pointer values will then point to the actual text data in the slice, which will be somewhere in memory. The problem is these pointer values will change over time. They only make sense for the current execution of the program, not even the same computer, it's not even the same across execution, it'll be just the same for one execution. And this is really bad for serialization because you want serialization, you want things you serialize to work everywhere. Unless we're going to snapshot the entire heap, these pointer values are completely useless for serialization. For zero-copy deserialization, we have to avoid having indirection in any of our types, which makes most Rust collections by default a bad fit because they expect pointers in them. So the solution here was we developed the zerovec crate. It provides the zerovec and zerovec containers that step around these problems. They're all internally copy on write, so there's no need to actually use cow with them. They kind of do that internally for you, because if you're doing zero-copy deserialization, you probably want cow. Zerovec is for variable size types like strings, and zerovec is for fixed size types like U32 or char. They both have designs that work around the problems mentioned here. Zerovec works by only accepting types that implement this trait called as ULE, which means they have a corresponding ULE type that they can be converted to and from. And ULE stands for unaligned little endian, which describes the nature of the type. Firstly, it must have no alignment requirements. It can exist at any point in memory. And secondly, it's expected to have the same representation in memory regardless of endianness. Because most systems are little endian, we just recommend that you maintain the little endian representation so that getting it out of memory on little endian platforms is basically free. For example, if you're looking at a zerovec of U32s. The ULE type will be something like that, just an array of 4 bytes, which is aligned, which is byte aligned and has no endianness requirements. This type has the same representation of all platforms. Under the hood, the zerovec would then be similar to kind of like a slice of these types, looking something like that. If we take the U32 slice we were looking at before, its zerovec would kind of contain like these arrays with this kind of memory representation. But when you fetch elements from the zerovec, they just get converted back. So users don't actually see this internal type. They just see these nice, the normal type they wanted, which was U32. On the other hand, var0vec works by using kind of a special data format where all the data is splatted into a single contiguous buffer, and the metadata header tells you where to find the data. Similar to zerovec, it requires var_ule types, which are variable length types that can be encoded in the same kind of unaligned little endian format. For example, if you want to make a var0vec of strings and have it represent the same pair of strings from before, it would look something like this in memory. The first 4 bytes marks that it contains 2 elements, and then the next 2 bytes kind of are the internal offsets of each element. When indexing, var0vec will do the appropriate calculations to return the correct pointer. Zerovec and var0vec support some pretty complex types, and they can be nested deeper. For example, we've already seen that you can use zerovec with a fixed size type, and var0vec with a simple variable size type like stir. But you can represent types like a nested vector of U32s, a nested vector of strings, an even more nested vector of strings. We also support maps, which are internally built out of sorted zerovecs. Someone's actually working on a hash map that's zero copy using perfect hashing. That's a rather cool thing if anyone wants to look at it later. You can also use custom types in these structs. Manually implementing the ULE traits is tricky and also unsafe, so we have some convenient proc macros that do the hard work for you. For example, if you want a zerovec that contains this kind of custom date type, you can slap this zerovec make ULE macro on it, which generates an internal ULE type like this. You don't really need to care much about it, but it generates this, and the repr packed means that it has no alignment requirements. It's the repr packed plus the fact that all of the fields have no alignment requirements means that it has no alignment requirements. Because all the fields don't care about endianness, it also doesn't care about endianness. If you substitute the actual ULE types, it looks something like this. But again, the user doesn't need to care about what's going on under the hood. It's just now hooked up and they can use this directly. If you want like a custom month info type, then you can slap make var_ule on it. And then you have to use the corresponding var_ule type in the zerovec. This is slightly different from before, since instead of using the normal type, you have to use the generated var_ule type in var0vec. There are a couple of reasons behind this. You can ask me after the talk, but yeah, it's just slightly different. This generates an unsized type like this. The last field is an unsized string, which means this is a dynamically sized type. In Rust, if you do this, then this type can only exist behind a pointer. And it also generates convenient conversion functions between the two so that you can kind of cheaply view the latter type as the former type when you need it. Zerovec tends to deserialize around 10 times faster than regular vectors. var0vec's exact wins are far more variable since they strongly depend on the size of the elements, the complexity of the vectors, and whether you're using kind of SerDes support for zero copy deserialization as far as you can take it without using these crates. While not shown here, the performance of reading from the zerovec types is slightly slower than regular vectors. For individual reads, it rarely matters. It tends to be 20% slower to sum all of the elements in a zerovec if you're trying to read everything. That's one of the heaviest operations you can perform. So it's more of a worst case scenario. Otherwise, basically, we don't notice it. In ICU4X, all of this turns out to be a net win. Shane's talk had some nice graphs showing serialization costs basically go away. Yeah. Using zerovec, we've managed to make all of ICU4X's non-experimental data work in zerocopy. This covers more than 50 different types of data, covering a lot of different data keys. ICU4X can guarantee that there will never be allocations when loading data, which is pretty good. Would be remiss of me to talk about zero-copy deserialization without mentioning archive. Archive's a crate by David Kolosky. It came out a couple years ago. It provides a lot of the same benefits using a rather different kind of holistic approach. It's really cool, it's super robust, and it's worth checking out if you're working in this space. The main reason why we don't use archive is that archive is its own serialization format. We want to use SerDes, we want to have control over the serialization format because we want to be very flexible around data. We want to support JSON, postcard, bin code, XML if you want, anything. Archives derives also end up creating kind of their own parallel versions of the types for everything. So it's far trickier to write code that works both with archive and SerDes, especially if you want to keep the code size low, which we care about quite a bit. But for a lot of use cases, archive is great and you should check it out. All right, we solved one limitation. What's next? Another limitation is the pervasive lifetimes it introduces to the program. For example, the date symbol data might look something like this with a tick data lifetime referring to where the data was loaded from. Context is just a type kind of that covers whether it's long, short, medium, whatever. The type doing the formatting might then look something like this, and it'll contain a loaded copy of the data, and it's using the lifetime to mean the same thing. It might have methods that look like this. I have more, when you construct it, you need to also know about the tick data lifetime. And then it might get used like this, where you have to hold on to the data provider without moving it for the duration of time you're formatting data. You end up with a lot of tick data lifetimes everywhere. A lot. Besides being annoying, lifetimes prevent us from using more complex data management strategies. For example, we might want to have a data provider that, let's say, dynamically loads data from the network or disk. It only wants to hold on to loaded data as long as it's needed, which can be a variable period of time not known at compile time. Individual data users may even need it for different lifetimes. For example, the user might load data for a date formatter. The different part of the code base might also want a date formatter. Then they might need to load data for a number formatter, some other formatters, all from different areas of the code base that don't know too much about each other. They could then go out of scope at different times, perhaps with one of the date formatters going out first, but then the other one still needing the data, followed by some other stuff, followed by the final date formatter going away. We want the data to stay as long as it's needed, but not longer, and we don't necessarily know these lifetimes at compile time. It gets even more interesting if we want to add a cache to this, hold on to the last 10 bits of data even if no one's using it right now. Most of these are strategies that you typically implement in both Rust and C++ using some form of reference counting. But hold on. Reference counting is typically an alternative to lifetimes. You can use reference counting to replace code that's got lifetimes, but then the lifetimes have to go away. Zero-copy deserialization, as we've seen so far, needs the lifetimes. It mandates them because it needs to be able to mark that it's holding references to a subset of some other type. We can't just switch over. In Rust, using dyne to go from compile time types to runtime types is called type erasure. What we needed here is a way to go from compile time lifetimes, that is regular lifetimes, to runtime lifetimes, that is basically things like RC and ARC. We need lifetime erasure. Enter yoke. With yoke, you can mark zero-copy data like cow or a more complex object and say that it's borrowing from some data source, which we usually call a cart, by kind of yoking them together. The tick static lifetime is not actually accurate. It's just the cleanest way to represent an erased lifetime. But the end result of this is a type that doesn't impose any lifetime requirements outside of its use. There's no tick data or anything. You can use it and you don't need lifetimes everywhere. The way you use it is that you first kind of load data from somewhere, perhaps into an RC to enable the lifecycle flexibility we were talking about earlier. You might do some fancy caching thing, who knows. Then you construct a yoke out of it by calling yoke attached to cart with a closure that deserializes the data from the cart. This object can be moved around, cloned, etc. It will safely hold on to the cart as long as it goes out of scope. You can perform all your caching if you want. And finally, you can kind of get access to the inner type by calling .get on it. It doesn't deref because get has an interesting signature, but now you have this type. Your yoke is no longer tied to the compile time lifetime of data. You can return your yoke, you can do whatever, and it's all fine. The magic here is behind the signature of get. The full generic signature is rather gnarly, but here's what the signature of get for a yoke of date symbols looks like. It basically shortens the inner lifetime to that of the local borrow. You can see that there are two ticks there. There's one of the borrow, and then there's the one of the inner reference. And that keeps it safe because this pins the lifetime of the yoke to as much as you're using the get for. And as for that period of time, all those lifetimes are valid. And then after that, you can move yoke again, and you can call get again and get new lifetimes. Yoke can only wrap types implementing a trait called yokeable. It's tricky to manually implement, but there's an easy custom derive available. Unlike most custom derives, it doesn't even require the structs fields to implement the trait, so it tends to be less kind of infectious than most custom derives in a code base where you typically just have to slap them on everywhere. There are a couple edge cases around complex generics, but most of the time it just works. Yoke supports some more advanced operations too. You can kind of project a yoke down to the borrowed data contained in it to get a different yoke that's pointing to a subset of the data if you want to kind of split things up. You can even copy on write mutate local data inside a yoke, which feels it feels like it shouldn't be allowed, but it does work. It is safe. The lifetime machinery, the trait-bound machinery required to make that safe is very scary, but it is safe. Going back to the code we had earlier, all this put together means that the core data type still has a lifetime, but then the lifetime's gone everywhere else. And you can kind of pass around objects like date formatter, like normal owned objects, because they don't contain any lifetime, so they're not really bound to any scope. So how does this work under the hood? Well, it's a bit complicated. Users of the crate don't really need to worry too much about this due to the custom derive. It just kind of works. But if you peek under the hood, you'll get to see some very gnarly things with some weird trait bounds and lifetime. Yoke kind of bullies the compiler into letting it transform lifetimes this way and letting it know that the lifetimes are safe to transmute. The process of developing yoke involved us discovering around 12 complicated compiler bugs. Properly explaining yoke would require me to say confusing Rust jargon like covariant lifetime and higher rank trait bound. And I'm not going to inflict that upon y'all today. I do have a more in-depth explanation up on my blog, which I'll link at the end of the slides. And I'm happy to talk about this after the presentation. All right, so far we've made zero-copy deserialization work for more things. We've made it more pleasant to work with. Ultimately, it still involves deserialization. What if we could get rid of that entirely? Wait, what? That doesn't make any sense at all. How can you avoid deserialization during data loaded? Why would you even want to? The whole point is to load the data. That's what deserialization does. So stepping back a bit, with libraries like ICU4X, you need to load a lot of data. That data can be loaded from memory in many different ways, but deserialization is the most flexible. But sometimes you know the data beforehand when you're building your application. If you care about startup times, you might not want to pay the deserialization costs, even if they're not as slow because of zero copy. You could construct that data manually in Rust and just stick it in a static, but anytime that data changes, you have to change your Rust code manually. One of ICU4X's users is Firefox. Browsers really care about startup times. Startup times, page load times, all these like initial stuff. People care about that. They may need to load internationalization data dynamically, so they still need our pluggable data loading stuff. But there's also a bunch of stuff they just always need. They just know that they need this internationalization data all the time. It's not great to have to pay that deserialization cost on startup, a time where slowness is so noticeable to the user. The thing you kind of want to do is deserialize a bunch of data into a static. Like, it would be really cool if this worked. It doesn't, because no deserialization library in Rust is const, and Rust const support is not far ahead enough to be able to do this, though it might be in like a year. We could write a very unsafe serde deserialize, kind of something that looks like serde deserialize, but is very unsafe, and it operates on fully trusted data and skips all validation. But you still kind of need to scan the data to pick up all the pointers and load them. It's generally very tricky to also rely on the data always being trusted. What we need is a serialization format for Rust that needs no validation, needs no scanning to find all the pointers, and can be loaded safely. This sounds like an impossible set of goals, but is it? There's such a format that already exists and has existed for years: Rust code and statics. Loading compiled Rust code in statics is just a pointer read, since the format on disk is exactly the format Rust uses to store these objects in memory. If we can serialize Rust values to Rust code that can work inside a static, we're good to go. We've basically made the Rust compiler itself a part of the serialization process, because you're just converting to Rust code and the compiler is converting to data that just can be loaded for you when you compile your binary. Enter databake. Databake is a crate we designed for this purpose. It contains a trait called bake with the following signature. Basically, values of type that are bake can be serialized to Rust code that compiles to those same values. Databake doesn't require that code to work in Rust's const context, but we do require that in IC4X because we plan on using that in a static. It comes with this simple custom derive that can be slapped onto most types, provided that most fields implement the trait. You do have to tell it the path of the type, though. It's a bit annoying, but it's generating Rust code, so it needs to know where it lives. Calling bake will generate code that looks something kind of like this, with the individual fields filled in by the bake implementations of those types. Here's a real-world example of the output for the data we use to format numbers for Bangla. Our data generation code needs to do a bunch of work to wrap this and hook it up to the data loading machinery. But most of the databake output in IC4X looks kind of like this. It's like moderately readable most of the time, but it's not supposed to really be read. So IC4X's CI builds test data in around 20 locales for everything we support, just for test purposes. This data turns out to be a 3.9 megabyte blob in Postcard. Well, it's 20 megabytes of JSON. When using databake, it turns into 32 megabytes of Rust code. This is large enough that when we first did this, it crashed Rust Analyzer, and we had to kind of like opt it out or do something so that Rust Analyzer wouldn't go looking for it. This data is ultimately code, and the optimizer can get rid of dead code. So it's actually kind of hard to measure the impact on an actual binary, because all of this depends on how exactly you're using it. The compiler will just get rid of things it doesn't think you're using. It's around half the size of the Postcard files from some like relatively unscientific attempts at measuring this. Take that number with a grain of salt. It's really hard to get an accurate measurement. An additional win from using databake is that if you're only using databake, your binary doesn't need to include any deserialization code. So you get another size win there. As Shane mentioned earlier, we really care about code size. We want to be able to like run on embedded platforms that don't have much space at all. Here's similar data for just the stuff you need to format dates and times for the same 20 locales. So just kind of more of a subset to the data that we've been talking about so far. So with databake, we've given users the option to thoroughly yeet deserialization overhead within IC4X. All in all, we've achieved 3 goals with 3 different crates. Firstly, we've made deserialization completely zero copy with the zerovec crate. We've also made zero copy deserialization pleasant to work with the yoke crate. Finally, we've made deserialization unnecessary in certain situations with the databake crate. To quote one of the greatest Christmas movies, "And when Alexander saw the breadth of his work, he wept, for there were no copies left to zero." Thank you.
Thank you, Manish. Do we have any questions about cows and baking and related topics?
I didn't fully understand from your talk. I mean, you showed basically a very nice concept. I didn't really understand how much what you finally achieved is the concepts you, let's say, invented, or from Rust giving you the possibility to learn.
Oh yeah. So the question was how much of the work here was stuff that Rust is really good at, and how much were the crates, like stuff we invented in the crates. The concept of zero copy deserialization is one that has predated Rust. People do it in C++. It's trickier to be safe for it in C++, but people do it. So that's been around for a while. It's been around in Rust for a while too. And there are already crates that achieve some of the things we want to do here, just in a very different way that might not work for us. And Rust specifically is very good around zero copy deserialization because lifetimes mean that it's very hard to mess it up. Normally, you either have to do lots of reference counting or whatever to be safe, and that too is often tricky to get right. It's easy to still mess it up in C++ in stuff I've seen. And with Rust, like because of the lifetimes, you can be very, very loose about how you're dealing with data because you know the compiler will catch you if you do anything wrong. So you don't have to be too cautious, which is good. So zerovec is that kind of way of solving zero copy deserialization problems it's a very old established way. Zerovec is a way of fitting that into Rust's model and Zürisee's model. So that it is Rust specific in that way, but the ideas of, oh, you need to kind of have a metadata thing for indirection, you need to deal with alignment, endianness, these are old concepts. The yoke thing, it is extremely Rust specific because it is kind of, it's solving a problem you can only really have in languages like Rust where lifetimes are a thing, because in other languages, you would either probably have just designed it to be always reference counted or always cached, like very pervasively, which would make it less generally useful but safe, or you would just be using references and just be like, be careful, don't mess this up, or you'd have a GC. So the yoke is very Rust specific, but this is kind of us extending the thing of zero copy deserialization in Rust lets you be much looser in what you're doing, much more flexible because you're not worried about messing things up. And yoke is kind of pushing the boundary there. And databake is something you could do databake for C++. C++ has constexpr as well. Rust only recently got a very flexible constexpr. It's been in the works for ages. It's been on nightly for a while. Only recently has it been to a point where you could do a lot of the things here. So that is, I haven't really seen anything like databake before, but that's not really Rust specific. That's just languages with constexpr. There aren't that many, especially compiled languages that compile to things without a runtime like Rust and C++. That's already a small set, and out of them, Rust and C++ both have constexpr, but I haven't seen stuff like this before. So that is a newer idea, not necessarily specific to Rust. It would be cool for someone to do this in C++. Custom derives in Rust make life so much easier because that for C++, I mean, you could use like a Clang plugin or something to do the same thing, but custom derives mean that we can kind of just do this. It's just part of the code. You just slap these attributes around and you're kind of done. First.
Do you see or know about yoke? Is it something or which would be included in standard Rust?
The question is, could yoke be included in standard Rust?
Or concepts from it, like?
yes, and yoke itself is kind of specific. This has to do with yoke's implementation, but being able to talk about lifetime variance in trait bounds in a way that doesn't require me to do a custom derive and stuff like that would be kind of nice. So in the long run, having magic compiler traits that are implemented on that let you kind of sniff the lifetime variance of a type would be very cool. Some of yoke's complexities are made simpler by generic associated types. Yoke does not use generic associated types because we wrote it before that were stable, but those things do help. Not that much unless also the compiler came up with ways of talking about lifetime variance that's useful in those contexts. So yeah, yoke itself, I don't see that ever making it into the standard library. None of the crates here, I think, would make it into the standard library. The standard library tries very, very hard not to be too niche, and mostly takes things that really benefit from being common across ecosystems. And yoke doesn't. There are other crates that do self-referential things like yoke. There's Ouroboros, which is another good one. It doesn't have the same goals, and it would not be useful for us here. But if you're doing things like that, that's another crate to look at. So there are a bunch of different strategies for doing this, and they have different pros and cons. Yoke works really well for what we want to do, which is erase lifetimes and zero copy deserialization. I think there was a question back there.
What's the compile time like with your macro generating 32 megabytes?
Oh, the question was what's the compile time with the macro generating 32 megabytes of Rust code? The macro does not generate 32 megabytes of Rust code. The macro generates a small amount of Rust code that can be called. And when you call that Rust code with all of its kind of functional dependencies, with all the data, we already have a lot of data. Part of this is like, we have a large amount of data. The number that was on the slide was like some number of megabytes of it was like a couple megabytes of, I don't remember anymore, but it's a large amount of data. Yeah, it was like 300 kilobytes of postcard, right? And that's all the data in a very compact format. And that's for 20 locales. And so some of that's just, we have a lot of data. We don't generate that data at compile time. The ICU4X, the way you use ICU4X is once you know what data you need, you run this tool called DataGen. You say like, and there's the static data splicing stuff Shane talked about earlier, so you can kind of give it a binary and give it, like, I want English and French, English, US, and French, or whatever. You like give it a bunch of locales and it'll generate data. And then you also tell it what kind of data you want. And it can be a postcard blob, it can be a JSON thing, like set of folders. There are a bunch of different ways to ask it for data. One of those options is databake. So basically, you run it once, you get some Rust code, you make that a part of your build toolchain, you make that, like you put that in a crate or put that in a module or put that somewhere. And then you only need to update that stuff when you're generating new data, which should not be that often. Like you might need it if you're adding a locale, or you might need it if you want to update to the latest CLDR data, or if you're kind of patching data with your own kind of changes. So yeah, if DataGen, the data generation step is not super fast, and we have not ever tried to really optimize it much because it's not supposed to be run that often. Otherwise, yes, it would take a little while. Wouldn't actually be that slow though. Like it's still something we could run it in the build process, and like you would just notice the build being kind of slow, but it would not be like, oh, the build is taking 2 hours. It would just be like, oh, why is the build taking 5 minutes? Yeah. Okay.
Question is performance. When you do zeroalization, zerovec versus normal string, especially in the cases what I've seen in the data, you have a lot of small strings, but a lot of them.
Yeah.
What is the performance difference roughly between zerovec and the normal?
The question was the performance difference between zerovec and a normal allocated string for a slice of small strings. My understanding is that the slice of small strings is still like faster, It's not 10 times faster like zerovec, but it is like more like, I think 2 times faster for that kind of case. It actually, yeah, for like a small one. If it gets bigger, then suddenly it becomes more expensive. It also kind of depends on the allocator you're using and some other stuff. So yeah, I don't think I've seen zerovec is never like the zerovec is never slower than the original thing to deserialize. Of course, it can be slower to read, so the actual net cost is harder to calculate. But it tends to be, like I said earlier, it tends to be. It's almost always, as far as I can tell, it's always been a win in ICU4X.
Well, does yoke also work with multi-threaded code, or is
Yes.
there an assumption?
The question is, does yoke work with multi-threaded code? Yeah, there's nothing in yoke that assumes multi-threading. I was using it with an RC here. You could use an ARC. In ICU4X, we kind of encapsulate all of that. Like in ICU4X users don't need to care about yoke. We have some other types that kind of encapsulate all that. So ICU4X actually, for that, we use a cargo feature so that you can turn on like sync versus non-sync reference counting, because but we technically could make that more pluggable. Like generically abstracting over sync and non-sync is very annoying. So, and it would be pervasive. So we didn't do it that way. But yeah.
Any more questions? I was wondering if could Zürisee be extended with some of this, like the machinery from the zerovec, and make it easier? So you just say borrow the normal way.
It could. I think some of this becomes now you've made Zürisee more opinionated.
Oh, yeah.
Because Zürisee is very happy to have these kinds of things work. It works very nicely with these. It wasn't hard making this work with Zürisee. You just have some serialized and deserialized symbols. And we can we've made a lot of opinionated choices here. I suspect Zürisee would not want to take this. And I think also someone could write something similar that has different trade-offs used for a different purpose. For example, one of the trade-offs we've made is we really do not care about serialization performance. The zerovecs are cheap to make, but zerovecs they're actually not that slow to make, but they are definitely much slower. It's like because of the metadata, so you can't really manipulate them like normal vectors and expect the same kind of performance behavior. You can still construct an entire zerovec from an existing vector pretty cheaply, but if you want to do stuff like if you want to like push and pull and insert and pop, that's going to stack up really quickly. And that's a trade-off we've made, and we're fine with it because we really don't care about how slow serialization is, but someone else might, and then they can design a different crate. We actually also, technically the format used is pluggable now, so technically speaking, you could actually plug in a different like format with different trade-offs into zerovec, but you could also just write your own crate. So yeah.
Any more questions? Then let's thank Manish for the talk.